So recording. So just as a quick reminder, last time we finished talking about the geometry of concave mirrors. Oops, where'd my mouse go? We were talking about concave mirrors, and I mentioned that I defined what the center of the mirror is. It's where the center of the sphere would be if you continued the sphere. I defined what the vertex of the mirror is. This is where the optical axis, which is that center line, intersects the actual mirror. And then I mentioned that because we're interested in objects with physical extent, in order to get some sort of well-defined measurement of where the object is, we need to treat the mirror as if it's very nearly flat. And the reason we do that is because we need to make sure that measuring the position of the object, the distance of the object from the mirror, is the same regardless of whether or not you measure from the top of the object to the mirror or the bottom of the object to the mirror. And the only way that happens is if you treat the mirror as not curving sharply. So we're going to be using that flat approximation going forward. It doesn't significantly affect what's happening. It's just, the point is you don't have to worry about the actual distance changing as you move along the vertical part of the mirror. It's always assumed to be occurring at that center line. So going forward, we can then ask the question, okay, I'm recording. We can then ask the question, for a concave mirror, how do we figure out where the how do we figure out where the image is? I need to fix that in my notes. Let me note that really quick. There we go. So if you put an object somewhere, how do we figure out where the image that's produced by that mirror is? For a flat mirror, we can do that. We can just draw a few rays, and then we know using the angle of reflection where those rays will go. Sorry, from the law of reflection, where those rays will go, and then we can backtrace them to the location of the image. We need to do the same thing here, but it's a little bit more complicated. So to answer this question of where the image is, not how big it is, we'll answer the how big it is question later. We can simplify, and instead of just looking at an extended object like an arrow, we're just going to look at just a single point along the optical axis. And so the reason why we can do this is because from the flat mirror approximation, whether it's on the optical axis or not doesn't matter. The horizontal position along the optical axis is the same regardless of whether you're at the top of the arrow or the bottom of the arrow. That is, spherical mirrors don't bend images. They will keep the image vertical if the object is vertical. So we can just imagine putting a single point on the optical axis, and then the location of that single point will be the location of any object that is at that point. Sorry, the location of the image formed from that single point will be the same as the location of an image formed by an object at that single point. So the picture here is you have your mirror, you have your optical axis. By the way, there's going to be a lot of drawings today. They're not going to be very good. I'm going to do my best to make them as good as I can, but I don't want to waste a whole lot of time on it. So all of these drawings will have corresponding like good diagrams in the lecture notes, or at least most of them do. So here's our center. And let's just say that we slap a point down here. We're going to put our object here. Our object is just a point. So let's just start drawing diagram or drawing rays. So let me get out the straight line drawing tool. Oh, by the way, I'm going to use a convention where green is incoming and red is outgoing. So here we have one ray coming off of the object, and we're going to need a few dotted lines to help us. These are dotted lines that connect the center. Actually, I'm not going to use dotted, I'm going to use black. These are dotted lines that connect the center to the point of impact. And then from the law of reflection, we know that this angle should be whatever the reflected angle is. So if we wanted to do this right, it would look something like this, just matching those two angles. Something like that, right? And the point then is that these angles are the same. Now we can do the same thing for another point, because if we want to figure out where the image is, then we could then we want to find points of intersection. But really, this is enough, because if we're clever about this, we could just say, well, wait a minute, why don't we just draw an image or a ray straight? We know that that's going to hit the mirror perpendicularly, so it will reflect also perpendicularly. So the point of intersection, where the image is formed, is right there. Now, as I mentioned when we were talking about spherical refractors, or rather, when we were talking about spherical refractors, there's this business that Snell's law makes it so that the point of convergence isn't exactly a point of convergence. The different rays will only approximately converge there in the small angle limit. The same is true here. So again, because this is a spherical refractor or spherical reflector and not a parabolic reflector, which is what you would need for exact convergence, all of the different rays will only approximately converge on that point. Once you start looking at very high angles, they will get further and further away. But for the most part, using the small angle approximation, they just all will converge at that point. So if we were to draw more rays, they would all bounce and pass through that single point. So the question then is, where does this occur? Now, to answer that question, we actually need to do some serious geometry, right? So I'm going to use the flat mirror approximation here. I'm going to draw a picture, draw a bunch of pictures actually. So here's our mirror. Our mirror is flat, as in the flat mirror approximation, kind of makes sense. Our optical axis is, say roughly here. So by the way, this flat mirror is actually curved, like it's actually something like this. We're just treating it as if it were flat. This mirror has a center, say here. And we're going to put an image. Here's our center. We're going to put our image here, or sorry, our object here, and we're just going to start doing some geometry. So let's say that let's say that we have a ray that comes from the object and bounces off, say, I don't know, here. So we're going to call this angle alpha. Fine. Now we need to do the same thing for a ray from the center that ends up at the same place. Call that angle beta. Greek letters, by the way. And then we know that these angles are the same. The angle that comes off the reflection. So I'm just going to do an approximation here. That looks about right. These angles are the same. And I'm going to call this angle gamma. So this point here, that is the image, that is the location of the image. And this distance is s prime. It's the distance, well, it's the magnitude of s prime, but we're just working with distances here. That is the location of the image. Similarly, this distance is s, it's the location of the object. And then the distance to c, that is the radius by definition. So you can do some geometry here. It's a little bit involved, but and we can call this distance, say, h. You can do some geometry here. It's a little bit involved, but the end result is that we end up with that alpha plus gamma is equal to twice beta. Is s prime positive since it's going out? Yeah, so in this case, according to the sign conventions, s prime would be positive, yes. So there's a geometric proof of this in the textbook. I'm not going to go over it because it's a bit involved, but this is the end result. We get that the sum of alpha and beta is equal to twice the angle, or sorry, the sum of alpha and gamma is equal to twice the angle beta. Basically, beta is the average of the two angles, which kind of makes sense. And then we can apply the small angle approximation that and this is just for generic, say, phi, that phi is equal, or I'll use a generic theta, that theta is approximately equal to the sine of theta, which is approximately equal to this tangent of theta. This is not this specific theta, by the way, it's just a generic theta. I mean, it also applies to this theta though. So that gives us that alpha, well, alpha is the angle, and it's approximately equal to the tangent of the angle. So alpha is approximately equal to h, which is the opposite, divided by s, the adjacent. So alpha is approximately, well, I'm just going to use equal signs now because we're using the small angle approximation. This is equal to tan alpha, which is equal to h over s. Similarly, beta is equal to tan beta, which is equal to h over r. And gamma is equal to tan gamma, which is equal to h over s prime. Then we can just combine these equations and these equations to get the following equations. Now, by the way, here there are 4 equations. There are 4 equations, and there are 1, 2, 3, 4, 5, 6 variables. So we can't solve for them explicitly, but that's a good thing. The point is that we can write alpha as, well, okay, let me just be a little bit more explicit. We can just plug in alpha here, beta here, and gamma here. And what we end up with is 1 over s plus 1 over s prime is equal to 2 divided by r. The h is canceled between all of them. This is known as the mirror equation, the mirror equation. And it tells us for a curved mirror, and in fact, this actually applies for a flat mirror as well, where an image forms. It tells us what s is relative or given, sorry, it tells us what s prime is given s. Now, you might ask, well, what about the sign conventions? Now, in the above calculation, all of these quantities we computed, s prime, and so on, were magnitudes. They were distances. Distances are always positive. However, we can double check. According to our sign convention, I just want to make sure that I actually gave you the sign convention for the radius. No, I didn't. According to the sign convention, s is positive when it's on the incoming side. S prime is positive when it's on the outgoing side, and both of those are true. So s and s prime are both positive, and so we find that that this equation is valid so long as r, which is just the radius, is also positive. So this gives us actually another addition to our sign convention table. So now we can even attribute a sign to the radius of curvature. Which is r. So long as the radius of curvature is positive, this equation is valid for the picture that we just drew. And so, oh, okay, it's a cat licking himself. So we say that the radius of curvature is positive when the center, remember the center is that point C, of the sphere is on the outgoing side. We could have also said the incoming side here, but there's a reason why we're choosing outgoing side here. And we haven't yet encountered a place where the radius of curvature should be, the radius r should be negative. So I'm just going to put question marks there for now. Now, just as an aside, if the object was to the right of the mirror center, for example, if we put our object, say, where the image actually is, or rather, if we put it even closer, say we put it like here, doing the same sort of calculation, we would have actually found out that s prime had to be negative. We would have ended up with a negative s prime. So I challenge you to actually do that. See what happens if you put an image here. And that's just basically because the angle is too big, so it reflects off, and you'll end up with convergence over on the other side of the mirror. And so what that means is that in that case, the formed image, where you put the object very, very close to the mirror, the formed image is to the right of the mirror. It's not on the outgoing side. So this actually gives us a new concept, which we kind of ran into when we talked about planar mirrors, which is that images which are formed, and I got to write this down in words, sorry. Images formed by light rays actually converging. So remember, images are formed by either light rays converging at a point where the object or where the image is, or appearing to diverge from a point. So images formed by light rays actually converging, meaning the light rays actually go to that point. These are called real images. That is when S prime is positive, because just like in this case, the light ray actually converges on a point. It converges on the point of the image. Those formed only by apparent convergence, i.e., it looks like there's light rays that are converging on the other side of the object, say on the side where light never actually goes, it just appears that there would be light rays converging there. Are virtual. These are virtual images. The takeaway here is when S prime is greater than 0, we have real images, because that means that the light rays are actually getting to the point where they're appearing to converge. Remember, S prime is positive when the reflected light, or when the outgoing light is on the outgoing side. Sorry, S prime is positive when the image is on the outgoing side, which means that the light is actually on the same side as the image that's formed. So the light passes through the image. Whereas when S prime is negative, that means that the light is that the image is not on the outgoing side, which means the light never actually gets to that image. So in that case, when S prime is negative, we would have a virtual image. Now, in neither case, for virtual or real images, is there like an object there, right? Like it's just a nomenclature. But the point is that for real images, it looks like you could reach out and touch it. Whereas for virtual images, it looks like it's too far away for you to reach out and touch it. Like, for example, if you formed a virtual image in the mirror, you would say, oh, well, there's a mirror in the way. I can't actually grab the object in the mirror because there's a mirror in the way. Whereas if there was a real image formed by a mirror, like in this concave mirror case, it looks like the image is actually in front of the mirror. And so it looks like you could reach out and grab it, even though you can't, of course. So the calculations that we just did, they tell us where an image is formed for a concave mirror, but that's not all we care about with regards to images. We also care about how big the image is, what orientation is the image. And so let's consider that. Let's try to figure that out, because we certainly need to know how to do that. So to do that, we're first going to consider the parallel ray case. So the reason why we're considering parallel rays is because it allows us to do something really sneaky. So when I say parallel rays, I mean that you have rays coming in that are parallel to the optical axis and parallel to each other. This kind of phenomenon happens when the object is really, really far away. So like if an object is sufficiently far away, all of the rays from that object are basically going to be parallel with each other, right? Because they'll basically all just be like, the picture is you have your object, rays that are, I can't even draw this to scale, but like the idea is if an object is really, really small, let's say that this is like 10 miles, right? All of the rays that get to the optical setup are going to be basically parallel. They're going to be really, really close in angle. And as this object gets further and further away, those rays those angles get even smaller. So when we say we're considering parallel rays, this is like saying, imagine you placed an object infinitely far away from your optical device. Then what happens? Well, so for mirrors, there's a special reflection, which only occurs for parallel rays. So we have our curved mirror, we have our optical axis. I can't draw the object here because it's infinitely far away, but I can draw the rays that come from the object. So here's C. And we have an incoming ray, maybe it looks like this, but it's parallel to the optical axis. We have another incoming ray, say, looks like this, also parallel to the optical axis. And the point is that for a mirror, these rays all happen to reflect in a particular way. they all reflect, regardless of what height they're coming to, they all reflect so that they intersect at a very particular point. So this point here, this is called the focal point. So the incoming rays, or when the incoming rays are all parallel to the optical axis, all of the outgoing rays intersect at a position that's exactly halfway to the center. So this f is equal to r divided by 2, like that distance. Let me draw that. F being the focal length. The focal point is one focal length away from the mirror. Let me write that out. This is the focal length, which is the distance from the mirror to the point. And so by using this particular equation, we can actually simplify the mirror equation significantly. Remember, the mirror equation was this guy, but this is just 2 over r is just 1 divided by r over 2, or 1 divided by the focal length. So this simplifies our mirror equation. And the reason why we're using this notion of focal point instead of the center is because every optical device has a focal point. Not every optical device has a center. So it's a useful generalization. So it looks like 1 over s plus 1 over s prime equals 1 over f. This is our new version of the mirror equation. They're both still valid. It's just one is written in a different way. It uses a different variable. So this particular phenomenon can help us do something that will let us calculate a height. So a height and an orientation. So before we do that, I need to introduce this notion of ray tracing. So let's talk about ray tracing. So ray tracing more generally is just this phenomenon of shooting out rays from an object, seeing how they interact with the environment, and then tracing where they end up. That's basically what we've been doing. This would be an example of ray tracing. We shot out some rays, in this case they were parallel rays, and then we let them interact with the environment, in this case a mirror, and then we figured out where they ended up. So ray tracing can help us, using geometry, figure out where and how high an object is. But there's a particular kind of ray tracing that is super powerful. This is this notion of principal rays. With principal rays, we can actually do ray tracing by hand for sufficiently simple optical systems. So ray tracing with principal rays involves following special principal rays. So instead of shooting out rays in all directions, we shoot out rays in particular directions. From an object until they become outgoing rays. So using this tool, the observer can conclude where the outgoing rays appear to originate from. And that lets you conclude where the image is. So just to be clear one more time, principal rays are not physically special. They're just some rays, but they are convenient mathematical tools. So what I'm going to do is I'm now going to show you I'm going to do my best to do a good drawing, a principal ray analysis for a concave mirror. So we have our optical, oh boy, that's not starting out, not a great start. Have our optical axis. I want to put the center like here. I'm going to put an object, say here. And keep in mind that the focal point, because the center is there, the focal point is halfway to the center. So this place here, roughly, that's F. It's our focal point. Okay, so there are 4 principal rays for a concave mirror, and there's 4 principal rays for any curved mirror, or for any spherically curved mirror. We'll talk about convex mirrors in a minute. The first principal ray is a ray that reflects through the focal point. So I didn't choose this order. This is the order that's in the book, and I want to be consistent with it. So this is a ray that reflects through the focal point. So the incoming ray passes through the focal point. Now we can use reversibility of this notion. If you shot a ray going this way through the focal point, then it should come out parallel. And that's precisely what happens to this principal ray. So the result of this principal ray is that it reflects, precisely perpendicular or parallel to the optical axis. The second principal ray, oh no, I got that one backwards. Sorry, that's not the first principal ray. I knew that felt weird. Sorry. The first principal ray really is the ray that goes parallel to the optical axis. That's not coming from the, come on. Okay, I'm gonna make the object a little bit taller because otherwise it'll be really annoying. Put the object right here. There we go. And then we can use the reasoning that we just had. Rays coming in parallel pass through the focal point. That's how the focal point is defined. Come on. There we go. Good enough. Okay, second principal ray. The second principal ray hits the center and then bounces off at the same angle, right? If it hits the center, the angle that it makes should be the same above and below. So this one's a relatively easy one to figure out. It just hits the center and comes out at the same angle. Hits the vertex, not the center. I need to use the right terminology. So roughly like that. Oh no. It's not what I wanted. Something's wrong. What did I do wrong? Well, I mean, it's not that I did anything wrong. I just want to have room. So it should be something like that. I'm going to extend the other ray because we know that they're going to have to intersect. I'll just draw it by hand. Sorry. Yeah, that's probably what happened here. But this is just a rough approximation. Ooh, that's terrible. No, I'm going to draw a line. Oops. This is the first example of a ray trace, so I want you guys to see it like done right. Good enough. Okay. Okay. Third ray, it passes through the focal point, and it comes out parallel for the same reason that if it goes in parallel, it'll pass through the focal point. Oh, this is going to be so bad. I'm sorry, guys. If I could do this with a computer, it would be a lot better. All right, change of plans. Instead of trying to draw this because it's going to come out terribly, I'm just going to show you the diagram that I was trying to draw anyway. Let me just pull it up, and I'll walk us through it. I won't just show you the diagram and then take it away, because it takes time to process. Spherical reflectors. Oh, does he not have the principal ray analysis? Okay, here we go. No. Here we go. Okay. All right. Okay, so here we have an object. We're doing our first principal ray, the one that goes out parallel and goes through the focal point. Then one passes through the focal point, comes out through the center. A third one, and then I need to pause this somehow. I have an idea. I'll just print screen. All right, print screen. Now I can share that paint document. Okay, here we go. Right, so the first principal ray, oops. A little bit bigger, please. There we go. Okay, first principal ray is the one that goes out parallel and then reflects through the focal length or through the focal point, right? So this is a paint stream, great stream. This is the first one. The second principal ray is the ray that goes or that hits the center and then reflects off at the same angle. See how this middle one, it goes to the center and then the angle is the same above and below? That's just because it's using the law of reflection. Third principal ray is, is the one that passes through the focal point. It's basically the opposite of the first principal ray. It passes through the focal point and then comes out parallel. And then the fourth principal ray, it's kind of hard to depict. It goes through the center, reflects off of the mirror, and then goes precisely back through the center. Now, the reason that happens is because the line that connects the center to the mirror is precisely perpendicular to the surface of the mirror. Otherwise, otherwise it wouldn't be the center, right? The center is what you get when you draw perpendiculars, and they all converge at the center. So from the law of reflection, that ray just bounces back in precisely the same line. This is just shooting a light beam precisely at a flat mirror, basically. So those are the four principal rays. And depending on the curvature, where you put your object, those rays will look different. To be clear, the order of the principal rays is not particularly significant. But the point is that they all have different descriptions. So the first principal ray you might describe as the incoming is parallel and the outgoing passes through the focal point. The second principal ray is the incoming hits the vertex, the outgoing reflects at the same angle. The third principal ray, you would say the incoming passes through the focal point and the outgoing reflects parallel to the optical axis. And then the fourth principal ray the incoming passes through the center and the outgoing passes through the center. So it's those kinds of things that are useful. The ordering doesn't actually matter. But what we can do, and I'm going to share screen again. And by the way, so if you guys want to like follow along and keep a look at that diagram, you can pull it up on the LibreText. It's in section 3.6, I want to say. Okay, right. The second one. So the second one. Let me do a zoomed in picture of the second one just really quick. So you have your object, you have your mirror. So it's very hard. So I can do actually good geometric optics in person when I'm using a blackboard, but on a piece of or on a tablet, it's a lot harder. So the second one is basically it's reflecting off of this surface here. So this surface, well, the way that we figure out what angle, like if we were looking at this one, we would draw a dotted line to the center, basically a perpendicular. And then we would say, okay, the angle of reflection has to equal the angle of incidence, right? So this angle would reflect that way. But for the case of the one that bounces off the center, well, that just means that this angle has to match this angle. They clearly don't match, but they're supposed to. These angles should match because the dotted line that passes through the middle is the one that hits the center. So just the angle above should be equal to the angle below. And that's just from the law of reflection, that the angle of incidence is equal to the law to the angle of reflection. Okay, so the whole point of this is that you can use these sorts of diagrams to do a ray trace and basically figure out where an image is. Now, you often don't need all of these. No, holograms are a lot more complicated. You often don't need all of these to figure out where an image is. In fact, usually you just need two, because so long as you know where the point of intersection is, then that's enough. But sometimes finding one is harder than finding another, so having four accessible is a good thing. Now, we can use this to understand how the magnification of an image relates to its position. Remember, magnification is the height of the image divided by the height of the object. So let's do a quick ray trace for, or I'm not even going to do all 4 rays. I'm just going to do one of them. So here's our object. Let's say our center is here. So I'm just going to do the ray that passes, or that bounces off the center. So it would be something like this. And its reflection would be something like this, right? Now, I don't know where, sorry, let's make this right. There we go. I don't know where the image is, and we could figure out where the image is just by doing one more diagram, but we don't need to. Let's just say that the image appears here, just for example. We know that it has to appear somewhere below, right? And we can, actually, let's just figure out where the image is, just so then we can, just so then it doesn't look like I'm just guessing. The image would be like about, yeah, maybe there. Let's get rid of that then. Okay, so the image is, say, here. Here's our object. So we know that that image is a distance s prime from the mirror, right? And the object is a distance s from the mirror. And we also know that this angle theta is the same as this angle theta. That's from the law of reflection. And that's also from the definition of that ray. So if we look at these triangles, I'm going to do them in, say, I will highlight them. If we look at these triangles, we see that those triangles are similar. They have the same angle. They're both, they have the same 3 internal angles, because one of them is a right angle, one of them is theta, the other one has to be determined to be the same. And so because they're similar triangles, we can actually relate the ratios of their height to the ratio of their length. So from similar triangles, we get that the magnification, which is y prime divided by y, I need to fix something in my notes. There should be no apostrophe there. This should be equal to the magnitude of s prime divided by s. Now, the only thing that we have to be careful about is that, well, according to our sign convention before, m is negative. Actually, let me write it this way. The magnitude of m is equal to the magnitude of y prime divided by y, which is equal, because these are all distances, right? This is equal to the magnitude of s prime divided by s. So this is great. This tells us how much the thing shrinks or grows. However, this doesn't actually tell us what the sign is. But we know from this picture that the sign should be, or that whatever we get, whatever formula we end up with, should end up with a negative magnification here because it's inverted. M is negative. And we also know that both S and S prime, or S prime and S, are both positive in this case because they're both, the S is on the incoming side and S prime is on the outgoing side. So what that means is that the formula for magnification should be the negative of S prime divided by S. And that indeed is our formula for magnification for a mirror. And you could check this, that this would work for any image that's formed for any spherical mirror. And in fact, this is just generally the magnification for most optical devices that have the image and the object both in air. We're going to talk about having the image or the object not in air in a minute, but when they're both in air, this just generally is the magnification formula. Now, just as an aside about this whole principal ray business, it's not like the light only goes from the object along the principal rays. If you put your eye somewhere between 2 principal rays where the output is, you're still going to see something. It's just the one of the principal rays doesn't get to your eye, but there's still all of the other rays that come from the object. It's just we're only interested in calculating with those principal rays because those are the easiest ones to calculate with. Now, just as a word of caution, if an object is between, if it's between the focal point I'm going to need to draw a picture here, so I may as well write this out. So if the object is between the focal point and the vertex, this is for a concave mirror again, the principal ray passing through the focal point, remember one of them passes through the focal point, right? And then it reflects off perpendicular or parallel to the optical axis. It doesn't start on the object. The principal ray passing through the focal point and I'm going to draw a picture to describe this. It starts at the focal point and passes through the object. And the same thing is true for the center point. If your object is closer to the mirror than the center point is, then the line that would pass through the center point actually starts at the center point and goes through your object. So the picture here is something like this. You have your mirror, optical axis. Let's say that your center is here and your mirror and your focal point is here. If your object is here, here's F, here's C, then one of the rays is going to be a ray that you would want it to pass through the focal point, but it can't go backwards because it has to reflect off the mirror. So instead, what we do is we just have it start through the focal point and go and then pass through the object. And then the same thing happens. It reflects off parallel. Similarly, for the center, the one that passes through the center, it also starts at the center and then ends up at the object. And then the reflection, because the one that passes through the center bounces off the same angle, the reflection comes back in the same direction. So this is it just can be a little bit tricky with how to do these principal ray diagrams for different locations of images. So I just wanted to make sure that this is clear. Oh, I guess I had. Oh, okay. I guess I can get rid of, well, okay, I have some editing to do of my notes. So by the way, this formula, this is the magnification for mirrors, but it's also the magnification for lenses, which we're going to see later, but I'm just going to call it the magnification for mirrors for now. And this is the magnification for all mirrors, concave, convex, or flat. Okay, there is an example that I linked, so go check that out if you're interested. Otherwise, we'll continue on to another type of mirror, which is a convex mirror. Convex mirrors are a little bit harder to wrap your brain around, or maybe not. So a convex mirror is just the opposite of the concave mirror. The concave mirror is the one that it looks like if you were to walk to it, it's like you're walking into a cave because it curves on you. A convex mirror is the one that just bulges out. Sorry. And a lot is the same that we did for convex mirrors as it is for a lot of what we did for concave mirrors also applies for convex mirrors. The only difference between these two is that the normal to the surface, remember the normal is what determines the law of reflection, so that's why we care about the normal. The normal to the surface is on the other side of the mirror. That is, the line connecting the mirror to its center is on the other side of the mirror, not the side that things actually, where light actually goes. So a picture looks something like this. By the way, we're almost always going to put our object, or at least our first object, on the left. So if we have an object somewhere here, and say here's the center, well, our light is going to come off, say it hits that point of the mirror. Yep, I dropped the word normal. So the way that we would figure out what angle this light ray bounces off at is we would draw a normal. Now, the normal is the line that connects the center to the to the point of interest. So it's, say, this line. Come on. I wish that there wasn't like a gridlock. So the point then is that the line that we're drawing, the line that we use to determine our line of reflect, or our angle of reflection, is this line. And then that just tells us that the reflected angle should be, you know, the same angle both ways. So let me actually draw this in red, because that's the, it should reflect that way. And so that this is the only difference. And oh, I drew this. Okay, let me actually, I'm going to fake this and pretend that the angle is less severe than it actually is. It's called, just so that I can draw a point. There we go. And that's actually probably more accurate. And so that line, maybe it's a little more at an angle there. To make these dotted, can't hurt. This point here, this would be where the image is, because that's where the rays would appear to converge. Again, you can find that out by shooting a ray perpendicular to the, by shooting a ray up perpendicular this way. Right. So they would appear to converge behind the mirror. The point is on the left, is on the right side of the object here. Sorry, is on the right. The object is on the left side of the mirror, and the image is on the right side of the mirror. And so this is the phenomenon that happens for convex mirrors. Often, and actually always for convex mirrors, the image will have to be found by tracing the rays back to some point of convergence. Because if you just looked at this ray, and if you just looked at the this ray and this ray, you would say, well, those don't even converge. But you have to trace them back to some point that they never actually went to figure out where the apparent image is. Because if the mirror wasn't here and instead the object was at this location, it would produce rays that go off in those directions. And so that's why the image appears to be there, because that's the direction that the rays appear to be coming from. Now, so in this case, the sign convention for R and F are both negative. We'll get to that. Here, S prime is negative, because S prime is not on the outgoing side. It's on the other side. But just to be clear, for a convex mirror, the rays will always appear to diverge. If you were to draw another ray, it'll diverge away. If you draw another ray, it'll always diverge away. And so the lesson then is that the images formed are always virtual for a convex mirror. Meaning that they always are on the other side. Now, ideally, we would use the same mirror equation that we had just a bit ago to determine where the images are. It would be really inconvenient if we needed to have a separate mirror equation for convex mirrors compared with concave mirrors. So the question is do we have to modify it? And the way to figure this out is just to think about the focal point, because, you know, just this type of mirror should also have a focal point. It just might not be on the correct side. So we're going to, again, consider a very large or a very distant object. Very distant object with S approaching infinity. That, which again tells us that the incoming rays are parallel. So just like before, we figured out that the focal point is the location where parallel rays converge to. So we can do the same thing here. We have our convex mirror. We have incoming rays. Draw them parallel. Now, these rays are going to deflect off at some angle. We can figure out what that angle is, but the end result is that, oops. The end result is that they converge. Sorry, let me do this right. There we go. Not right about there. And now I just have to do some erasing, so you can tell what are actual rays and what are not. So the dotted lines will typically represent rays that are not actually getting to that location. They just look like they're coming from that location, right? So the actual rays just bounce off and diverge, right? However, they appear to converge here. And you can do the exact same divergence. This is the point of apparent convergence. You can do the exact same calculation that we use to figure out where the focal point is for a convex mirror here. And we find that this point, F, is precisely R over 2 if this distance here is C. It is precisely still halfway again. It would be closer in, sorry. Like there, maybe. It would be, again, half of the radial distance. It's on the other side. And it's on the other side because the center's on the other side. If you were to complete this circle, right, the center would be on the other side of the mirror, not on the side that it's bouncing off of. So the focal point is also on the other side of the mirror. So the question then is, if the image is always virtual, that means that S prime is always negative. And so we also know that S prime, when the object is infinitely far away, we know that the magnitude of S prime, where the image appears to be, is equal to the magnitude of R over 2. I'm just putting magnitudes everywhere because we're only talking about distances. So we can check our mirror equation by plugging these in. So we know that, to be clear, this implies that S prime is equal to negative magnitude of R over 2. Because S prime is negative, we don't know what R is, whether R is positive or negative or whatever, but we can just check now by plugging it in. So we plug into our mirror equation S prime, and we're going to figure out what R is. So we have 1 over S, which is 1 over infinity, plus 1 over negative magnitude of R over 2, which is S prime, should be equal to 2 divided by R. Now, 1 over infinity is 0. And so this tells us that because this term is negative, R also has to be negative. This tells us that R is less than 0. And that further, because F is equal to R divided by 2, tells us that F is also negative. So the only modification we need to make in order to make our mirror equation work for a convex mirror is we just need to use the appropriate sign conventions. So we can fix our sign conventions. I'm just going to go copy them. You guys can add them to your tables. If I were doing this in person, I would have one blackboard that has all of the sign conventions on it at all times, but I can't. So the radius of curvature is negative when the center is on the other side. So when it's not on the outgoing side. And then we can even add one more symbol. We have the focal length, which is symbolized by the letter F. And it has the same a very similar sign convention. When the focal point is on the outgoing side, it's positive. And when the focal point is on not the outgoing side, when it's on the other side, then it's negative. And using those sign conventions, now we can use the same formula for both convex and concave mirrors. The only thing that changes is the sign that you have for F or R, if you're using the version that has R, is just, it just differs by a negative sign. So F is just a number that happens to be negative for a convex mirror. Now, ray tracing gets harder for convex mirrors. So I'm going to show you another diagram. I'm not going to draw it because this one would be a mess and a half. Let me see if I can print screen it again. At the perfect time. Okay, there we go. All right, hold on, I can share now. Yes, so in this case, the sign convention are both negative. Is that the what to the point of the left? Yeah, okay. Yeah, those were all the questions. All right. So here we can go through the principal rays. So here it's a little bit different. So our first principal ray would be the ray that so our first principal ray, it comes from our object. Just like the other one, it goes in parallel. Now, the thing is it can't pass through a focal point over here because the focal point isn't on this side. What instead happens is it bounces off in a direction that if you continued the line through, it would pass through the focal point. Let me make this slightly smaller so that, can I not zoom out slightly less? Okay, that's, sorry, I know it's small. Right, so the point is that the ray bounces off in a way, oh, that's a very, very thin pencil. In a way that if you continued it through, it would pass through the focal point. I'm doing this with a trackpad, by the way, so don't hate me. So that's still the same. It's just instead of the ray actually passing through the focal point, it just appears to have passed through the focal point. Our second ray is the same as before. It just bounces off of the center and then comes back out at the same angle. So that's not surprising. It just does that. That's just because it's hitting the mirror at its center where the perpendicular is perpendicular to the, or is in the same direction as the optical axis. And so again, we want to figure out where it appears to have come from, so we continue it backwards. And we'd see that it appears to have come from something that emitted a ray in this direction. The third ray is one that, third ray is the ray that is aimed at the focal point. So before, if the focal point was, say, here, the third ray would have come through, passed through the focal point, and then reflected off parallel, right? But here, the focal point isn't on the correct side, the positive side of the, or the incoming side of the optical setup. So instead, it's just aimed at the focal point. So if you were to, so it comes in this direction, and it's just directed as if it were going to pass through the focal point. Of course, it can't because there's a mirror in the way. But then it reflects off perpendicular, or reflects off parallel, because it's aimed as if it did come from that that focal point. And then the fourth is the ray that's aimed at the center. Again, if it did pass through the center, then it would be going perpendicular to the surface, so it reflects off in precisely the same direction. So it goes back the same way. And so then the point is you trace all of these back, all of these rays that we just created, and you find that they intersect, or they would intersect at a point if you could trace them back. And that point that they all intersect at tells you where the top of the arrow ends up. And so you can do this sort of analysis, or you can do this sort of ray tracing for any type of mirror. You just have to know which type of, depending on the type of mirror, depending on whether the focal length is positive or negative, you have to know what type of ray tracing to do. You guys are going to get practice with this. This is going to be hard. I can almost guarantee you that there will be a ray tracing problem on the second midterm. Like just here's a setup, do your principal ray analysis. So get practice with this. It's a really useful tool, and it helps you visualize what's happening when otherwise you would just have equations. So, take a look, do some practice, find some practice problems. So again, this is also in the LibreTexts, just at the bottom of the same chapter. So go take a look at that if you want to still have it up. Otherwise, I'm going to share screen and continue on my notes. So just as a note, because we could do the ray tracing for the convex mirror. Well, the way that we found the magnification for the concave mirror was by doing this ray tracing using similar triangles. The same holds true here. The magnification obeys the same formula. Because for identical reasons. And you can check the sign conventions work out. If the magnification for a convex mirror is also negative s prime over s. And so here you'll see that because s prime is always negative and s is usually positive, here the images that are produced are upright. And so if you've ever looked at like a bulbous mirror, it'll just look like there's a smaller thing off in the distance. It's upright, it's not inverted. Whereas if you looked at like a concave mirror, like if you look in a spoon, your face is inverted. But if you look on the other side of the spoon, your face isn't inverted, it just looks smaller, but still upright. And so if you plug in a negative sign for s prime, you'll get that m is positive. And indeed, the magnification checks out for the exact same reasons. So that's basically the gist of spherical reflectors. So you can have concave, convex, or planar spherical or planar reflectors. That's basically all of it. Now you could stack a whole bunch of them like one after the other and get something complicated, but that's just a matter then of doing this process over and over again. There's another type of phenomenon that we investigated last time, which was refraction. If you have a planar surface, like the surface of a swimming pool, we figured out that if you have an object in that swimming pool, we can figure out where the image is. This is for a flat surface, but what if the surface is curved? Like, for example, what if you had a fishbowl full of water? Well, if you have a fish in your fishbowl, that fish will look like it's in a different place than it actually is because the surface is curved and there's a change in index of refraction. So we're going to study spherical refractors. This is section 4.4. Now, there's a lot that goes on here geometry-wise. We're going to skip over a lot of it because a lot of it's not particularly interesting. But if you guys like geometry, and geometry is really cool, by the way, like my job is geometry. If you like geometry, I suggest you go and try to prove these things. This is a useful exercise to do, but I'm not going to spend that time in lecture because it would take up the rest of lecture. So the question that we're trying to answer by talking about spherical refractors is what happens if the interface, the interface between the two media, is curved like a sphere? Think a fishbowl. So there are 4 possibilities. So the reason there are 4 possibilities, unlike in the mirror, is so for the mirror, there are 2 possibilities. It's either curved inwards or curved outwards, right? And we're assuming that the light is always, or that the object is always to the left. But here, not only are there the inward and outward possibilities, there's also higher and lower index of refraction. So one case would be something where you have N1 being less than N2, and you have light coming in this way. And this would be like a convex, or shaped like a convex mirror. This would be like the edge of a fishbowl, right? If water has a higher index of refraction, fish water, water. And the fish would be over here, and then there'd be a bowl shape, right? So another example would be the same thing, but with the indices of refraction reversed. So you have the same shape, you still have light coming from the left, but now you have N1 is greater than N2. Think, for example, if you had this would be a good example, a really big bubble of air in the ocean, right? You have an object that's in the ocean, in the water, and that light is going to pass that bubble. The bubble of air is spherically symmetric, and that the air inside has a smaller index of refraction. The other 2 possibilities are exactly what you might expect. They're concave shaped. You have light coming in from this side. You have N1 is less than N2. What would be a good example of this? This is like you have an object inside the air bubble, and then it's leaving to go into the water, right? That would be the example of that. And then the third example is when you have n2 is great, or n1 is greater than n2. Here you have your fish emitting light, and it goes out into the world. By the way, the fishbowl example doesn't work here because here you would put like your hand over here, and then we're asking what the fish sees, right? Whereas here you put your fish over here, and we're asking what we see. Sorry, your fish is over here. We ask what we see. Now, by the way, you guys probably have figured out already that these two are basically the same, just reversed, and these two are basically the same, just reversed. And that's true, like that just is true, but it's still useful to treat these as 4 separate cases, and then we're going to unify them all. Now, unfortunately, oh boy, that's a really messy diagram, and again, I don't want to draw it. Let me pull up the lecture notes really quick. Oh, you know what? Let me just go to the lecture notes and I'll just talk through the diagram real quick. Oh, too far. Not far enough. Here we go. All right, so let's start with the first case. So here you have like water in the gray, and then air in the white. This is, you have a lower index of refraction on the left, and you have a higher index of refraction on the right. And then you put an object on the left side. We always treat our objects on the left side. So the light that hits the center, from Snell's law, it will transmit through the surface at precisely the same angle that it came in with. And that's just because 90 degrees, like n1 times sine of 0 equals n2 times sine of 0. Like sine of 0 is 0. So the angle with the perpendicular is 0. So Snell's law doesn't affect things when they enter perpendicularly. So the blue ray or the red ray will enter and then pass through unaffected. The red ray, on the other hand, well, it will enter at an angle, and then we have to use Snell's law to see how much passes through the surface. Now, we're not going to worry about reflections here. We're just worried about what image, or what do people or objects that are on the inside of the other medium see. So we know that to apply Snell's law, we have to figure out what direction the perpendicular is in, and then measure the angles relative to that. So here, this dotted line, that is our perpendicular. And the angle θ1 is the angle that we would plug in into Snell's law, n1 times sine of θ1. And then the perpendicular is also here, the dotted line that passes through, and the θ2 that is pointed to by that dotted arrow is the angle that Snell's law would tell us. So for this particular example, because the index of refraction is higher inside the material than outside the material, we get that the light bends toward the perpendicular. In this case, the angle between the perpendicular and the light decreases. And so what we end up with is the beam that was pointing up redirects to point down towards a particular point. And so then we can figure out the point of convergence. And that point of convergence will just be wherever it is. By the way, this center C, that's the same center as it was for the convex. It's just, if you filled out the sphere or the circle, it's where it's the same thing. That point of convergence is just wherever it is, and it depends both on the index of refraction, and it depends on the location of the object, and so on, and the radius of curvature, all of those things. And we're gonna try to figure out where it is. We're gonna try to calculate what S prime is. Now, keep in mind here, if we're going to use the same sign conventions, the outgoing side now means something different. This is now the outgoing side. It is the direction that the light goes after it changes direction. And this is still the incoming side. So now, in this case, S prime is positive because the image that forms is on the same side as the outgoing side. And S is also positive because it's on the same side as the incoming side. Okay, so let's look at the next example, the next type of situation. Here, we have the same shape of surface, but here we have that n1 is greater than n2. So in this case, from Snell's law, we would see that light will bend away from the perpendicular because it's going into a faster medium. Remember, if you have a slow medium and a fast medium, then, and here's your perpendicular, then light going here will bend away. This is what happens for total internal reflection, remember. I want to erase that. Sorry. So we again just send one straight through. That will always pass straight through because it's perpendicular to the interface. The next thing, though, is what about the ray that we emit at an angle? Well, that ray is going to hit the interface and it's going to transmit at some angle, but those angles will have to be determined by Snell's law. Now, in this case, because the index of refraction is smaller inside the medium than it is outside the medium, the ray bends out more instead of bending in more. And so again, that ray just goes in the direction that it goes in. But the important part is that that ray, this blue ray, doesn't actually converge with the transmitted ray through the center. Instead, we have to imagine where would they converge if we continued them both. In that case, you continue them both back, and we find that they will appear to converge. The light that somebody over here would see, or the light that somebody over here would see, it would appear as if the light was coming from a point here, coming from that image point. So in this case, S prime is negative because it is on not the outgoing side. Again, this is still the outgoing side because light is passing through. And now the image is formed on the not outgoing side, i.e. negative. So S prime is negative. Similar, again, though, S is still positive. The next case, and by the way, this is all just qualitative that we're doing so far. Deriving the formulas that we're about to do is a mess. And so I'm not going to do it. I think it's actually done in the LibreText, but I'm not sure. I'd have to double check. Okay, so the next case is we now have the curve is going this way. This would be like a concave. It's shaped like a concave mirror, except it's an interface instead of a mirror. And we're asking about transmission. So put our object somewhere and just start tracing rays. So the one that goes straight through always goes straight through. That one's easy enough. What about the one that comes out at an angle? Well, the one that comes out at an angle, again, we have to use Snell's law. So this angle, theta 1, should be related to this angle. Here, come on, right, please. So Snell's law, or from Snell's law, we know that because it's going from a higher index of refraction to a lower index of refraction, fast or slow to fast, we know that it'll bend away from the interface. So this angle theta 1 should be smaller than this angle theta 2, which is exactly what you see in the diagram. And so you see that those rays will converge, and they'll converge at a particular point, and that is the location of that is the apparent source of the light. That is the place where the light appears to come from. If you were just looking here, you would say, oh, all of the light seems to be coming from this particular point. That's what an image is. Finally, we have the last case. Very strange case. We have a lower index of refraction inside our medium than outside our medium. We're going to put our object inside our medium, and we're going to ask, where does someone outside the medium appear to, or where does someone outside the medium think that light comes from? And here we're going to assume that, again, it's this concave type shape. So in this case, our parallel ray is our parallel ray, always goes the same direction, always goes straight through. Our not parallel ray, our angled ray, well, we have to use Snell's law again. So this angle is the angle relative, that's the perpendicular, that's the angle relative to the perpendicular. That angle should be bigger than this angle. The reason is because you're going from a fast medium to a slow medium. When you go from a fast medium to a slow medium, you bend toward the perpendicular. So this angle ought to shrink as it passes through. And so we can draw what those rays would be. This is, say, theta 2. This is, say, theta 1. And then we would see that, again, they diverge. They appear to spread out. So they don't actually appear to converge at any particular point on this side of the medium, or in that medium. So instead, we have to backtrack them both into the medium. And so for someone outside, outside of the medium, it'll appear as if the object is at a different place inside the medium. So this is the fish example. Yeah, this is the fish example. If you put a fish in a bowl, it'll have this very strange phenomenon. Well, perhaps I can find a video of that so you can see it, but this is not the fish example. This is just a different example where N1 is smaller than N2. This would be like a reverse fish bowl where you have a bubble of air surrounded by the ocean. So in this case, the image here is virtual. S prime is negative because the image is on the other side of the outgoing side being the right side. Now, the important thing to notice here is that the difference between the mirror and the refractor, the spherical mirror, spherical refractor, almost the only difference is that the outgoing side is on the opposite side, right? The outgoing side is on the side that the light gets to, and so because it's a mirror, because in one case you have a mirror which bounces light back the other way, and the other case you just have light continuing through, the outgoing side is different for the spherical refractor. Now, I'm going to go back to the notes I was writing so you guys can follow along. So we can use the same sign conventions. We established that R is negative if the center is on the, we have to be careful here. The sign convention that we established is that R is negative if the center is not on the outgoing side. So in this case, R is negative here because the outgoing side is over here. In this case, R is positive. In this case, R is positive, and in this case, R is negative again. So another distinction is that for the things that look like concave mirrors but interfaces instead, the radius has a different sign, and that's because it's not because the center moved. The center's still in the same place. It's because the outgoing side moved, because we're talking about transmission now, not reflection. And so if you use those same sign conventions that we've established, where S is positive if it's on the incoming side, S prime is positive if it's on the outgoing side, F and R are both positive if they're on the outgoing side, then we can actually just do some geometry and come up with some equations. The equation that we figure out for where the object is depends on the index of refraction, the location of the object, and the radius of curvature. And the equation that we end up with is N1 divided by S plus N2 divided by S prime is equal to N2 minus N1 divided by capital R. This is our equation for a spherical refractor. Now, I'm not going to derive that because it's a mess, as you can probably tell. It's really not that bad, but if you don't know exactly what you're doing, you're going to get stuck. Now, just as I mentioned, two of these situations are going to have diverging rays, and two of them are going to have converging rays. The two with diverging rays are these two cases. So here we would have diverging and diverging, and then we have converging and converging. Converging rays means that if you shoot rays in parallel, then they will come together at a point on the outgoing side. Diverging means that if you shoot rays in parallel, they'll spread out as if they came from some point on the incoming side, not on, or on the other side from the outgoing side. Now, that's all fine and dandy. This is a formula, but we kind of want to unify these in a sense, we want to unify mirrors or reflectors and refractors because they're both optical devices. So the fewer equations we have to memorize, the better. So let's try to figure out what would the equivalent thing of a focal point be for a refractor? Well, so mirrors have this special point, the focal point. The focal point for a mirror is the place where parallel rays all appear to converge to, or where they appear to diverge from, right? So if you shoot parallel rays at a concave mirror, you will get a whole bunch of the rays reflecting off will converge at a point. If you shoot rays at a convex mirror, you'll get a whole bunch of rays scattered off in a diverging cone, but they'll appear to have diverged from a single point. And that point is the focal point. So the question is can we do the same thing for a refractor? And the answer is yes. Well, the way that we handle this is we just ask the question the same way that we did for a reflector. The way that we did this for a reflector was we asked, okay, if the object is infinitely far away so that it emits parallel rays, the location of the convergent point or divergent point should be the location of the focal point. So here we say, if s prime, or if s is equal to infinity, then the rays are parallel. And so then we can solve for where the equivalent refracting focal point should be. So for mirrors, what we we do that here. We just use the refractor equation, the spherical refractor equation, we plug in. So we have n1 over infinity, that is the location of the object, plus n2 divided by f. F should be the point where they all converge. That should be the focal point. This should be equal to n2 minus n1 over r. And then we can just do algebra. This becomes 0. We can just do algebra and find that the focal point for a refractor is n2 over n2 minus n1 times r. So it's not quite r over 2, but it's related to r. This is the focal length for a spherical reflector. The focal length for spherical refractor. And so taking this and plugging it into our spherical refractor equation simplifies it. That means that n1, we can just replace r with f and adjust the equation accordingly. This gets us that n1 over s plus n2 over s prime is equal to n2 divided by f, which is a lot simpler. This is the spherical refractor equation. And then you could do the exact same thing for, you could do the exact same sort of analysis for magnification, because we want to find out what the magnification is for a spherical refractor, i.e. how big does the image grow or shrink. Again, you would have to use, you can't use similar triangles, but you can use, well, yeah, you can't use similar triangles, but you can use related triangles whose angles are related by Snell's law, in particular to rewrite the following. So and the way that I'm going to justify that, so okay, let me back up. So the way that we figured out the magnification formula for the spherical reflectors was by using similar triangles. The algebra is a lot messier for spherical refractors because the angles aren't the same. So you don't actually have you don't actually have similar triangles. You just have triangles whose angles are related by Snell's law. Now it's doable. You can do the geometry, but instead what I'm going to do is I'm just going to rewrite the spherical refractor equation in a way that lets us kind of steal from the reflector magnification. So the spherical refractor formula is n1 plus n1 over s plus n2 over s prime equals equals n2 over f. Then I'm going to divide both sides by n1. Sorry, divide both sides by n2. So what we have is we have n1 over n2 times 1 over s plus 1 over s prime equals 1 over f. And so now this formula precisely matches the formula that you would have for a spherical reflector, except the object is now at a different place. That is, this is exactly as if the object was at n2s divided by n1 plus 1 over s prime equals 1 over f. And then the resulting image for a spherical refractor located at s would give you the resulting image for a spherical, the resulting image for a spherical refractor with an object located at s would be at the same place as if you had a spherical reflector with the same focal length located at an image located at position n2s over n1. And so we can actually steal what the magnification was. We know the magnification for a spherical reflector should be at negative s prime over s. But here, s is this thing. So the magnification works out to be negative s prime divided by n2s over n1, which just works out to be, simplifying a little bit, magnification is negative n1s prime over n2s. And this is the magnification for spherical refractors. I know it's not a very satisfying derivation, but it does work out, and you can check the LibreText for more details if you're interested. Let me actually make sure that that's in there. Can't imagine it's not, but yeah, it is. Okay. Oh yeah, but he basically does it the same way. Yeah, that's fine. It's whatever. Yeah, it's image height divided by object height still. Yeah. That's always true. So I mean, that covers spherical refractors. We talked about the formula that tells us how to get them, or how to figure out where images are. That's the spherical refractor formula, or spherical refractor equation. We figured out what the focal length is, where the focal point is for a spherical refractor. And this is all using the same sign conventions that we've already established. And we figured out the magnification. That's all there is to learn. The magnification tells us the size and orientation. The spherical refractor equation tells us the location, and that tells us everything we need to know about an image given an object located somewhere to the left. That's it. So now we can do something different that we couldn't do with reflectors, and that's put two refractors together. So this is the discussion about thin lenses. So thin, not all lenses are thin. If you have bad eyesight, you'll find that your lenses are actually quite thick. However, for the most part, we can approximate them as thin, and that's what we're going to do. Thick lens results are complicated and messy, so we're not going to worry about it. So in general, like the only time you'll have to use the results that I gave you, the results about spherical refractors really, is like if you have a fish in a fishbowl. Like it's not often that you have an object in one medium and an observer outside of the medium and the medium is curved. It just doesn't happen often. I mean, it can be useful, but we don't care about it all that much. Instead, what happens more frequently is you have light in one medium, passes through some other medium temporarily, like a glass window or like a prism or whatever, and then it comes back out into the medium. Typically, it goes air, medium, then air. And so depending on the shape of the medium that it's passing through, what the index of refraction of that medium is, and so on, we can get different types of ray optics. You can get that the light rays bend in different ways. For example, you guys have all seen, well, you guys all know that we're talking about lenses here. Lenses are just pieces of glass that are shaped in such a way that they have curved surfaces. So it goes from air. You have an object in air, emits light, it passes through these curved surfaces. Now glass has a different index of refraction, so you'll get spherical refractive properties at those or inside the lens, and then it comes out at a different angle. It bends, and this is how you can get corrective eyeglasses. So the simplest case of a type of lens that we can form is just gluing two spherical refractors back to back. Like literally just take a spherical refractor, stick another spherical refractor on the other end, have the same medium on the outside and one medium on the inside. So let's talk about actually constructing lenses. That's exactly what we're going to do. By the way, not all lenses are just simple spherical refractors glued back to back. In fact, they're rarely glued. Usually they're just ground as a single piece of metal or material, or they're cast as plastic. But if you have optically clear glue, then it doesn't actually matter. So we're going to start by examining a double convex lens. Now, double convex doesn't perhaps might not mean what you think it means. It means that both sides are kind of symmetric. So we're going to take two converging cases. Oh, come on, erase. Erase, please. So we're going to take one of these with n1 is less than n2. We're going to have air here, say glass here. Then we're going to have glue. Then we're going to take one of these where we have n2 is greater than n1. And we have glass here. We have air here. So this is a double convex lens, even though you might see this as like concave. This one's certainly convex, but you might see this as concave. It's called double convex because of reasons, basically. Sorry, I should make this n1 is greater than n2. n1 is always on the left, n2 is always on the right. Now, the important point, though, if you remember from before, is that in the case where you had, in this case, that was one of the converging interfaces. If you had light rays coming in parallel, they would converge. Similarly, if you had light rays coming in parallel here, they would also converge. They're both converging cases. So by sticking them together, you're just getting an even more converging thing. And so what does it mean to glue these things together? You literally slap them together. And the end result is something that looks like this. It's a lens. It's the thing that is in your eye that lets you see. So we have N, maybe it's glass, maybe it's whatever, and then we have air on either side. Now notice that we don't have like a whole bunch of stuff between them. This is because we're doing the thin lens approximation. If they were really far apart, then it would matter. So here, and I've drawn this purposely lopsided because they don't actually have to have the same radius of curvature. They can have different radii of curvature. Maybe we have one radius of curvature here, call it C2, because this is the radius of curvature of the second interface. We have another radius of curvature over here, or a center of curvature called C1. And maybe C2 is, maybe R2 is smaller than R1. They can have different curvatures. Now, if you have a ray that comes in parallel, well, we need to figure out where does it go? Well, we know that for this interface, the angle that we have to refract it with, apply Snell's law with, is this angle. So we know that let me draw this in green, sorry. Parallel ray coming in. So we know that the refracted ray, well, we know it's going to converge, and we have to apply Snell's law. So Snell's law says that it should bend toward the normal. So the angle that it makes should be less steep. So that's the way it would. Sorry, that's not even right. That's what you would do for a reflector. What am I doing? Zoom in and clear this up a little bit. Stop erasing that. Okay, now my tablet's just freaking out. There we go. Draw small eraser. There we go. So we know that it will bend toward the normal, so the angle is smaller. And then, again, let me make that angle a little bit more dramatic. Oops, where'd we go? And by the way, I know we're very nearly out of time. I'm going to draw this picture, and then I think we're going to call it a day. Well, nearly. I have a little bit more to say. So maybe it angles off like this. Now we know that at that interface, the normal that it interacts with is this normal, the normal that comes from that center. So we have to draw that. And so in this case, again, it's going from a slow medium to a fast medium. So it should bend away from the normal. So this ray is going to bend even more downward. Notice that this angle here, so we have a whole bunch of angles. We have an angle here, theta 1. Then we have an angle here, theta 2. Sorry, it's not that angle. Oops. This angle is theta 2. Then we have an angle here, theta 3. So what we see is that if you shoot a ray parallel in to these two converging things stacked together, you get something that is even more converging. You have a parallel ray coming in, and it bends down towards the center line. It converges. Now, as with a mirror or a single refraction interface, like we saw above, all parallel incoming rays, will intersect at the same point. That's just true. You could try this you'd have to get out a protractor and do this right, but this is something that would happen. And indeed, that point is the focal point of the lens. So I'm just going to draw a little cartoon, and then we'll call it a day. So you have your little lens. What we're going to do is we're going to treat that lens as if it were thin. So we're going to imagine all of the bending occurs at this middle line. Then you send in your parallel rays. They're all going to converge at a single point. And this point here is the focal point. What we're doing here, by the way, just to be clear, is we're treating the lens as if all of the bending occurs at a single point. If it doesn't, then you have to worry about how far it's traveled inside the lens, which complicates things significantly. Or sorry, all of the bending occurs in a single plane along the center line. This is what's known as the thin lens approximation. All right. I know I went over, sorry about that. I'm going to stop the lecture here and